Hi, this is Arash and welcome to the Epoxy channel. In this channel, we're going to talk about the epoxy resins from the theoretical aspects to the most practical ones. So if this is the first video you're watching, or if you're interested in epoxy resins, please like and subscribe to our channel for more videos. Today, I'm going to present flexibilizer and tougheners for epoxy resins. The epoxy resins suffer from brittleness and have poor resistance to crack initiation and growth, resulting in poor impact and peel properties. In sealant formulations, epoxy resins do not often provide the desired elongation, and so properties such as flexibility and toughness must be improved. These problems can be overcome by either flexibilizing the epoxy structure or incorporating modifiers into the adhesives. Flexibility is primarily characterized by materials elongations. Flexibilizers in epoxy systems work by allowing the material to deform under stress, and the higher elongation yields higher peel strengths. In other words, flexibilized adhesives reduce mechanical damage by lowering the modulus and increasing elongation via plasticization. This increase in flexibility is mainly due to decreasing the crusting density of the cured adhesives. However, decreasing the crusting density results in lowering of certain properties such as tensile strength and glass transition temperature. Toughness, on the other hand, is characterized by a material having both high elongation and tensile strength, whereas flexibilizers work by deforming. Tougheners improve properties because elastomeric inclusions in epoxy matrix absorb energy and stop a crack from propagating. Toughened adhesives tolerate damage by preventing crack growth and thus limiting the damage area. This results in enhanced fracture impact and stress resistances with minimal change in the crusting density. Tougheners result in both features, resistance to impact while maintaining a high degree of temperature and chemical resistance. Flexibility in epoxies can be enhanced by several means. 1. By adding flexible chemical groups to the cured epoxy structures via either the epoxy-based resins or the curing agent. 2. By adding non-epoxy flexibilizing resins to the formulation to create an epoxy hybrid system. And 3. By adding flexible diluents to the base epoxy resins formulations. Adding non-epoxy flexibilizing resins to the formulation creates epoxy hybrid systems. Flexibility can also be embedded by adding flexible diluent to the base epoxy resins formulations. We also have flexibilizers that are used as additives to rigid epoxy resins either during the epoxy formulation stage or during the epoxy resin manufacturing process. They are generally reacted into the epoxy resins or have reactivity with various curing agents so that the cured properties are not significantly reduced due to the addition of the flexibilizers. These techniques are often used in epoxy adhesives formulations. A common technique of flexibilizing epoxy adhesives is by blending the epoxy resins with other more elastic polymers. Epoxy nylon, epoxy polysulfide, and a certain extent epoxy urethane hybrids use such a mechanism to provide flexibility. It should be mentioned again that employing these resins may reduce certain properties. Flexible hybrid resins improve adhesive properties, especially low molecular performance and adhesion to flexible substrate. They also relieve stresses within the adhesives by allowing the chain to relax after cure, as well as any stress can occur in the bonded joint during the use. A good example of flexible epoxy hybrid adhesive is epoxy polysulfide. The effect of the incorporation of polysulfide resin in epoxy resins on the impact resistance has been shown here. The effect of the incorporation of soluble thermoplastic polymer additions, for example epoxy nylon and epoxy vinyl, has been discussed in other videos. To recall, the combination of these resins with epoxy yields very tough and somehow flexible systems, but their use is kind of restricted because of their high viscosity and high raw material cost. Moreover, almost all these systems need to be handled at elevated temperature or as solvent solutions. Diluents are primarily used to reduce viscosity. However, some diluents also provide a degree of flexibility depending on the component's functionality and the molecular nature. This could happen based on two mechanisms. One, by introducing long-chain flexible molecules into the epoxy structure that remain unreacted after cure, or two, by introducing long-chain flexible molecules into the epoxy structure that reacts during the cure. The first mechanism consists of non-reactive diluents, and they may be considered mainly as plasticizers. Non-reactive diluents result in an overall degradation of the physical properties. The second category consists of reactive diluents, and they can be considered as true flexibilizers. The reactive diluents are generally preferred for structural application because they do not degrade and the properties will remain untouched. The second category consists of reactive diluents, and they can be considered as true flexibilizers. The reactive diluents are generally preferred for structural application because they do not degrade end properties as much as unreactive diluents do. Moreover, the flexibility resulting from diluents is not comparable with the flexibility resulting from synthetic elastomers. They provide a degree of resiliency to a normal rigid systems, thereby improving properties such as impact strain and thermal shock. In adhesive systems, they provide internal stresses and provide a degree of resiliency that is better suited for counteracting different thermal expansion rates between the adhesives and the substrate, and they also reduce the amount of stress caused by shrinkage during cure. Reactive diluents are more effective than non-reactive diluent for adhesive systems. Of the various non-reactive plasticizers for epoxy that have been investigated, dibutyl phthalate is perhaps the most popular. On the other side, monofunctional epoxy diluents are long-chain molecules that have one functional group that can react with the epoxy system. The long chain forces the molecules in the cured structures to be further apart, and this permits the cross-linked molecule freer movement under stress. In adhesive formulations, glycidyl ethers are the most common monofunctional diluents. These include butyl glycidyl ether and allyl glycidyl ether. Other effective monofunctional diluents are epoxidized vegetable oils, olefin oxides, styrene oxides, and pinene oxides. Di- or polyfunctional epoxy resins may be considered reactive diluents that provide a degree of resiliency, yet most preserve the inherent properties of the base epoxy resins. As flexibilizers, these diluents are often blended with the more reactive epoxy resins. The commercial flexibilizing reactive diluents are predominantly glycidyl derivatives like glycols, dimerized acids, or reaction products of dicarboxylic acid with epoxy resins. Modern flexibilizers to modify diglycidyl ether bisphenol A base include isocyanide monomers and prepolymers, silicon polymers containing amine termination, acrylic polymers with carboxyl termination, functional as liquid polybutane-diene derivatives, carboxyl terminated butane-diene acrylonitrile polymers, and etc. Flexibility can be provided by incorporating large groups in the molecular chain, which increases the distance between crosslinks. The reduction in crosslink density increases the flexibility or elongation of the resulting molecule, but at the expense of lowering the glass transition temperature. This, in turn, generally results in a decrease in tensile and shear strain, as well as a decrease in other performance properties such as chemical and heat resistance. Flexibility can be achieved within the cured epoxy molecule by 1. Using a higher molecular weight, more flexible resins. 2. Using a higher molecular weight, more flexible curing agent. And 3. Decreasing the potential number of cross-linking sites by either choosing resins and curing agents with lower functionality or varying the resins curing agent stoichiometry. The main reason for the greater flexibility is due to long-chain difunctional material that upon cure becomes part of the epoxy resins. The result is a single-phase flexible system. The disadvantage of this approach is a reduction in the crosslink density and consequently reduction in glass transition temperature as well as the heat and chemical resistance of the system. Both the epoxy resins and the curing agent components can be made more flexible by increasing their molecular weight. Polysulfides and polyamides curing agents are examples of long-chain difunctional curing agents that offer improved flexibility in epoxy adhesive formulations. There are many other examples of incorporating flexibility into the epoxy adhesives by appropriate selection of the curing agent. For example, by changing from hexahydrophthalic anhydride to hexamethylene diamine, one can double the impact resistance of the resin system and slightly increase the tensile elongation at break. Gross changes in flexibility of a resin system can also be obtained through a major change in the structure of the cured resin. Such changes include shifting from an aromatic structure to a more aliphatic hydrocarbon or reducing curing agent functionality. Insertion of long hydrocarbon side chains also can provide additional flexibility to the epoxy molecule. Cured epoxies without the addition of the flexible resins show elongation less than 2%. It has been mentioned that the flexibilizers work by reducing crosslink density. Although flexibility is improved, other valuable properties are reduced. Reductions in tensile strain and heat and chemical resistance are characteristics of many flexibilized epoxy systems. Employing tougheners in epoxy formulation results in an epoxy system having high impact and peel strain in case of adhesives and high impact resistance. This strategy also is commonly used for epoxy adhesives. Toughened structure adhesives generally have two distinct phases. The larger phase is the base resins and the minor phase consists of small, on the other 1 micrometer in diameter, distributed elastomeric entities. The addition of the second phase significantly improves fracture toughness by providing crack pinning and stress distribution mechanisms within the material. The elastomeric particulate phase is often thought as of a crack stopper for improving fracture toughness. A variety of toughening agents have been used to modify epoxy adhesives to improve peel strain and fracture toughness without significantly affect other properties of the epoxy-based resins. Generally, these modifiers can be classified into 3 types. 1. Reactive liquid rubbers. 2. Functionally terminated engineering thermoplastics. And 3. Inorganic and hybrid particles. Early structural epoxy adhesives were based on modified epoxy resins by liquid butanediene acrylonitrile polymers with terminal carboxylic groups. By using low levels of these liquid polymers, the fracture energy of the cured diglycidyl ether bisphenol A type epoxy resins increased by a factor of 15. After the cure is complete, the adhesive consists of an epoxy matrix with embedded rubber particles. The formation of a fully dispersed phase depends on a delicate balance between the miscibility of the elastomers or its adduct with the resins hardener mixture and appropriate precipitation during the crosslink reactions. The advantages of this toughening process is that the high modulus and Tg of the epoxy resins are not sacrificed. The butanediene acrylonitrile tougheners that have been especially used in both diglycidyl ether bisphenol A and diglycidyl ether bisphenol F epoxy resins are 1. Carboxyl terminated butanediene acrylonitrile CTBNs. 2. Amine terminated butanediene acrylonitrile ATBNs. And 3. Vinyl terminated butanediene acrylonitrile VTBNs. CTBNs and ATBNs are the most commonly used in structural epoxy adhesives formulations. CTBN is generally the elastomer of the choice because of its miscibility in many epoxy resins. The degree of toughness is determined by the crosslink density of the matrix, the elastomer particle size, and size distribution, the volume of fraction of the elastomeric phase, and the degree of adhesion between the epoxy matrix and the particles. In general, the elastomer must be pre-reacted or adducted with the epoxy. Adducts reduce the likelihood of early phase separation and maintain the solubility of the elastomer in the unreacted resin systems. For CTBN, the reaction is carried out at high temperatures, for example 150 to 160 centigrades, and usually in the presence of catalyst, which yields the epoxy CTBN adducts. Compared to unmodified epoxy, the toughened formulation exhibits significantly higher peel strength and moderately higher tensile shear strengths. One of the disadvantages of CTBN epoxy adhesives has been their high viscosity, which limits additional formulation options. ATBN liquid toughening agents are synthesized by the reaction of CTBN polymer with an amine. ATBN liquid polymers usually are not mixed directly into the epoxy resins component since cross-linking and shortened shelf life will result. ATBN adducts are often mixed with the curing agent component of two-component epoxy adhesives. ATBN tougheners also increase the ultimate tensile shear and T-peel strength and environmental durability using conventional room temperature curing agents such as fatty polyamides, amidoamines, and amine ethers. Various kinds of engineering thermoplastics such as polyether sulfone, polyether imide, polyaryl ether ketone, and polyphenylene oxide have been studied as toughening agents for epoxy systems. Unlike early epoxy hybrid adhesives, for example, epoxy nylons or epoxy polysulfides, these modern attempts use engineering thermoplastics, tough, ductile, chemically, and thermally stable polymers having a high TG. These are chosen to improve toughness and not to negatively affect the high temperature performance. Due to the high modulus and TG of the thermoplastic modifier, the modulus and TG of the thermoplastic modified epoxy resins will reach or even exceed the corresponding values of unmodified resins. In addition to improved fracture resistance, this modification leads to reduced shrinkage and cure. The thermoplastic resins are usually blended with the epoxy resins in a solvent solution. It was necessary to increase the compatibility and interfacial adhesion of the thermoplastic modifier and the epoxy resins. The problem of poor miscibility of the thermoplastic resins and poor processability of the final products are the main reasons that these materials have not achieved commercial success yet. The thermoplastic additives offer comparably better high temperature performance, but they are more difficult to formulate. As a result, the cost of these adhesives is generally much higher than that of other toughened epoxy mechanisms. Inorganic particulate fillers such as glass beads, fly ash, alumina trihydrate, and silica have also been considered as toughening agents for epoxy materials. In these systems, the fracture energy of filled epoxies reaches a maximum at a specific filler concentration. Brittle, hollow glass beads have been found to be both an extender and an impact modifier for coating and adhesives. There are several advantages from using preformed particles as toughening agents. 1. They can be manufactured relatively easy into the particles of different sizes. 2. They maximize the volume fraction of the toughening phase. And 3. They enhance toughness without any loss in thermomechanical properties. Nanoparticle systems such as multi-walled carbon nanotubes and modified spherical nanosilica particles have also been used to toughen epoxy resins without the loss of the properties such as glass transition temperature or modulus. I hope you found this video interesting and thanks for your attention. Please share your comments, thoughts or questions and I will come back to you soon. Thank you.